In Chapter 9, we're going to be developing nonlinear design models that are appropriate for higher level path planning. In previous chapters, when we developed models for the autopilot, we went through painstaking detail to linearize our system about a trim trajectory. However, when we're planning paths, we cannot ignore the nonlinear relationships in position. On the other side, we do not need the high fidelity that's needed for the autopilot. We're going to be planning over much larger horizons, and we don't need the minute detail. We can just assume that the autopilot's going to be doing its job. So in this video, we're going to review the architecture and see where this chapter fits in. In following lectures, we're going to discuss closed-loop models of the autopilot and vehicle motion. We're going to be then we'll look at kinematic guidance models that don't consider the actual forces and moments, and those models are what we're going to use for path planning. Then we'll also develop dynamics guidance models that have small consideration of forces and moments. So let's go ahead and get started. As we jump in, we'll review our architecture slide one more time. We can see that we've already developed everything below this line. So in chapters 9 is really a prep for the path following, which we'll start to do in chapter 10. And really chapter 9 is a prep for the path manager, and it's a prep for the path planner. So the models that we develop in chapter 9 we'll be utilizing for the rest of the semester. So as we look at this architecture, the path planner is going to be giving a series of waypoints to a path manager. The path manager is then going to be giving a path definition to a path follower. That path follower is then going to be communicating to our autopilot, which is what we've designed in previous lectures. So this autopilot takes as inputs the airspeed, the altitude, the heading, and also we can do a feed forward command for the roll. So all of these commands are what the autopilot receives. What we're going to be doing in this chapter is looking at how do we model this as a closed loop system. Because now our autopilot, we can trust that it's going to be doing its job. So we don't necessarily need the high fidelity of the dynamic models that we developed in chapters 3 and 4. Okay, so chapter 9 really bridges the gap between autopilot and then the path planning portion of the course. So when we come in here and we look at what do we mean by a closed loop system of the autopilot. So we've mentioned many times before where we have our X is going to be our state. And we have our positions, we have our velocities, we have our quaternion, and we have our rotational velocities. So we have all of these variables, and this is, right, we have 12 or 13 if we do Euler versus quaternion. And then we also have inputs to the system. Now again, the state is something that we don't directly control. We indirectly choose the state by looking at our inputs. So in our inputs, we had our elevator, our aileron, our rudder, and our thrust. So these were the inputs. These are the things we actually got to choose. Right? And as we develop this model, then we use this notation where we had a box. We come in here and we have our desired our inputs and our state. And we took our inputs and our state and we did our forces and moments. And we came out of here where out of our forces and moments, we got our force vector and our moment vector in the body frame. And then we developed our derivatives. And this helped us know what our x dot was. Then we say we use that, and I guess our x goes into there as well. We use our derivatives then to help us propagate f forward in time, or x forward in time. So we call this whole box x dot is equal to f of xu. Now, when we did the autopilot, we then wrapped a controller in here. Well, let me draw the controller first. Given our state, we have our controller, or maybe I should call it our autopilot. That's what's actually produced our state x, not our state x, our input u, right? And here it is a function of our state x, and the inputs to this guy right here, this is what we were talking about right up on this slide. So we said, let's give it our desired VA command. We talked also about our height command. Oop, not A. And if we look here, we also could give it a course angle command. And then we said we also were going to do a feed forward. So that's goes into our autopilot, right? And our state also goes into our autopilot. So we have this controller that takes that feedback state x. Maybe that's where I should link that up to. And we now have an autopilot that'll get us to this, our desired altitude, our desired airspeed, and our desired course angle. Okay, so what we can do, oops, is we can treat this as a full system where now over here, the red box, the inputs are our autopilot inputs. The outputs, we're going to get a state out. And now this looks like a closed loop system. So, or it actually looks, we're going to treat it like an open loop system where we have our inputs VAC, HC, and we'll do our course heading commanded. We have this closed loop system. And then we get our state x out. So we're going to look at, we could, option 1, option 1 is that we could just take this high fidelity model. We know what we could take our original x dot equals f of xu, and u is equal to some function of the commands. I'll put these commands, the autopilot and our state, right? So we can model the really high fidelity. So this is our really high fidelity. Or 2, and this is what we're going to be doing in this chapter, we're going to use or develop simplified models. And we'll say these are going to be models that are sufficient for our planning needs. And they're definitely lower fidelity. Okay, so that's what the option 2 is what we're going to be developing going forward in this chapter. Now you could take option 1, and we've already done all of the development for that, right? So chapters, really this option 1, we could get from chapters 3, 4, and I guess 5 through 6. So we could get those models, and if we need, we have this high fidelity model. And we use this, we use it for sim. So we've already developed that model. Now we're going to do simplified models to help us ease our burden of path planning. So as we look at this, we have some simplified dynamic models. And again, this is just a summary. We're designing the higher level autopilot functions. We need models that are easier to analyze and simulate. Again, we have a much larger span of time, and we need to be considering the nonlinearities that come in the position equations. Our models are going to capture the essential behavior of the system, so we need a high enough fidelity. We will derive reduced order, reduced complexity models suitable for design of higher level guidance strategy. So again, this is all talking about, sufficient for what's needed. So we do have two types of models that we're going to be developing. The first is kinematic, where we're going to utilize the kinematic relationships, and we're not going to consider aerodynamics and forces directly. And we'll also develop some dynamic model where we do apply some force balance relations to a point mass model. So we'll look at these different models as we go forward. And that'll be a wrap.